talking about calorimetry today. Calorimetry is measuring heat. And to do that, we use an instrumentation called the calorimeter. And there are generally two classes of calorimeters. The simplest type of calorimeter is just an insulated vessel with some water in it usually. And what we do is we carry out a chemical reaction inside the calorimeter, measure the temperature change in the water, and then from the heat capacity, the specific heat capacity of the water, we can make observations about how much energy was evolved from the reaction. A more specialized form of calorimetry uses what's called a bomb calorimeter. And the bomb calorimeter is again consisting of a water bath that's insulated, so no heat escapes to the surroundings. So we call this the system. And if any heat were to escape to the surroundings, it would be, if heat were to bleed away, then we wouldn't be able to make a very quantitative measurement of how much energy was evolved by the reactants. With the bomb calorimeter, we use a thick-walled steel container, and we place something in it. Say, suppose you're measuring the calorie content of breakfast cereal. You would put in a measured amount of breakfast cereal, screw the top on, and the top has electrodes that dip into the inside of the container to cause a spark so that we can cause the reaction to begin. They pressurize it through a valve with pure oxygen, which supports the combustion of the contents of the calorimeter. And then when the reaction is triggered, it's triggered inside, underwater, on the outer part of the remainder of the calorimeter. So when the reaction takes place, all the mechanical energy is prevented from taking place. You can't do work unless there's expansion. Because it's all contained within the thick-walled vessel, all of the energy turns into heat energy. And so then we have an effective way of measuring how much energy was contained, what the internal energy of the chemical inside the calorimeter was. A combustion reaction is triggered within the bomb, which contains the vigorous combustion reaction. And the thick-walled bomb contains the mechanical energy of the explosion, and it is converted to heat. The heat warms up the water bath and allows for quantitative measurement of the internal energy of the reaction. And then, of course, we can also find out what the enthalpy is with adjustments. For example, here is the type of experiment that one would do in a bomb calorimeter. It comes from our textbook, number 555. A 2.2 gram sample of quinone is burned in a bomb calorimeter. The heat capacity of the calorimeter is 7.854. When I say the heat capacity here, they're not talking about specific heat capacity, and that's why there's no mention of mass. It's a heat capacity that, for the whole calorimeter. In other words, to make the calorimeter temperature raise by 1 degree, you have to have an input of that many joules of energy. The temperature changes from 23.44 to 30.57. What is the heat of combustion of quinone per gram and per mole? And then they give you the chemical equation for quinone. Chemical formula for quinone is C6H4O2. So we use the equation Q is equal to C delta T. Notice there's no M. There's no M because the heat capacity of the calorimeter has been given in units of kilojoules per degree Celsius. It's already been measured. It's already known. So you don't need the specific heat capacity for this particular experiment. We enter the values, multiply them out, we get that there's 55.9 kilojoules of energy released by the reaction. Now we find out how many moles of quinone we had. 2.2 grams divided by its molar mass gives you that many moles, 2 times 10 to the minus 2 moles. And then we simply do the calculation. Roughly 56 kilojoules for 2.0 times 10 to the minus 2 moles gives you 2.75 times 10 to the 3 kilojoules per mole. You notice I put a negative sign there. The reaction is exothermic. The burning of quinone releases energy, so that's why you would have the sign convention placing it as a negative quantity. I should have put it over here as well. This would have been negative as well. So that's the exothermicity of quinone in terms of kilojoules per mole. We could also calculate it in terms of kilojoules per gram, and we get negative 25.5 kilojoules per gram. And I noticed after I finished the calculation that I had only done it to level of 3 significant figures. As it turns out, it should have been 4 significant figures because every one of the numbers we used here had 4 significant figures. So there's a little error, and that's why I wrote oops, should be 4 significant figures. Next, we'll take a look at an example of Hess's law in action. Hess's law states that if a reaction is carried out in steps, the delta H for the overall reaction will be equal to the sum of the enthalpy changes for the individual steps. So Hess's law can be used to predict the enthalpy of a reaction without actually doing the reaction. And to do the example, I used the combustion of methane. Very often, methane is used as a form of fuel where the combustion products need to not contain carbon monoxide. So because methane is a very small alkane, the smallest alkane, it tends to combust completely. So they'll use it, for example, in forklifts that have to work indoors where you don't want to be exposing the workers to carbon monoxide poisoning. The products, the byproducts of combustion of methane are only carbon dioxide and water, which are relatively harmless. So here's the balanced equation for the combustion of methane. These are the reactants, these are the products. And the reaction proceeds with a certain amount of release of energy. In fact, 890 kilojoules of energy is released when you combust methane. I think it's per mole of methane. And the way we portray that on an energy coordinate where delta H is on the y-axis, the reactants, methane and oxygen, are at a high energy level. They have a high potential energy. When you burn them, the products they produce are carbon dioxide and water. They're at a lower potential energy. So the difference in enthalpy between these two is 890 kilojoules. So I put a negative sign there to show that the energy is released by the reaction. But there's a second reaction that you could do with the same atoms. If you rearrange these atoms to form carbon monoxide, 2 water molecules, and half of oxygen molecule, you're sort of stopped halfway. And the concomitant release of energy is less. And then if you were to continue the reaction to complete combustion, it would also release the remaining amount of energy. You'll notice that 607 plus 283 gives you 890. And this is... Mr. Fernandez, line 101. Mr. Fernandez, line 101. This is Hess's law in a nutshell. The reaction can proceed to completion, or it can go in 2 steps to produce the same release of energy. An example of Hess's law can be used in number 5.61 in our textbook. You'll see that there are two reactions are given, and their enthalpies are known. And then what they want us to do is to use these 2 reactions to find out the enthalpy of this reaction. Well, the way we set it up is we sometimes have to reverse one or both of the reactions that are involved, so that when you add them up, they give you the same products and reactants. So what I did in the case of 5.61 is I reversed the first reaction, which comes out like this. And when you reverse the reaction, you also have to reverse the sign of the enthalpy. This reaction is reported to have negative 1,640 kilojoules per mole of P4O6 produced. But because I've reversed it and I've made P4O6 the reactant, I also changed the sign on the enthalpy. And I use number 2 as is. When I add the 2 reactions, I cross out anything that appears in the reactant, appears both in the reactants and products. So we see that P4 appears in the reactants in this reaction, whereas it appears in the products in that reaction, so I cancel it. Oxygen, 5 oxygens appear in the reactants on the second reaction, but only 3 oxygens appear in the products of the first reaction, so I can cancel them both and put 2 as the net. Anything that doesn't cancel is then rewritten, and then we add the two other quantities algebraically. So when you add these 2 numbers, you get negative 1,300, and that would be the enthalpy for the formation of P4O10 from these 2 reactants.